The unlikely event that you're not aware of it, there is a test coming up on Friday. It'll be a little bit more packed than we are today because attendance tends to be pretty good on test day. So I am glad you came today. We won't cover new material, but we will practice some problems, and practice is good. How was the practice exam? Yeah, okay. And a murmur came up. Okay, good. Good. I do like the practice exam. There are some nice problems on there. And I think that you can learn some things. If you did well, that's a good sign for things to come. If you didn't do well, you still have another 2 days to practice. So, all right. So, what do you need to know? That's usually the question that people like to ask. What do I need to know? And the answer is more or less, you need to know this stuff here. And so once you see it, it's like, oh, there's not that much. It's pretty straightforward. So, maybe I shouldn't say it's not that much. There's a lot to know. But you should understand, just starting here on the left-hand side, understand functions, the idea of level curves. Level curves are where we have a fixed height. It's like we're slicing with a plane, z equals k, and where do we intersect our surface that our function corresponds to. We have level curves, of course, for higher dimensional functions. We also have level surfaces. We do other slices. For example, if we fix one of the variables, if I fix x equals k, or maybe I fix y equals L, or something like that, I can work in a slice, and that's how we did derivatives. We said, look, derivatives are hard for multivariable functions, so what we do is we get them down to single variable functions by looking in slices, and then we're good to go. If you're looking for a range and domain of functions, just ranges, outputs. We tend to avoid testing on range because it's hard to actually find the range of a function. But the domain, it's easy. Look for your problems. Divide by 0, square root of negatives, log of something less than or equal to 0. Know how to take partial derivatives. Now, we're not going to test you on the limit definition of partial derivatives because I thought you had enough fun doing that in Calc 1. And we don't need to have that kind of fun. But you should understand the philosophy. The philosophy of partial derivatives says, hold one of your variables constant. Or really, I should say, if you have multivariables, something like 3 or 4, hold most of your variables constant. Only one is changing. And then take the derivative. Now, we see the partial symbol. The partial symbol is the same thing as the d symbol. It indicates derivative. The only difference is we have a function of more than function of more than one variable. If you hear the word differentiable, that intuitively just means it's locally flat. For us now, flat things are not lines, flat things become planes. And so we're going to talk about tangent planes in just a second. What does it mean to be differentiable? Well, we need the partial derivatives to exist and to really be continuous. And as long as that's true, then we're differentiable. All right, so here we go. This is an important idea because there's really two ideas here. The first off is the idea of the tangent plane. F of xy is approximately f of ab plus f sub x, and remember that's another notation for partial derivative with respect to x, at ab times x minus a, plus f sub y of ab times y minus b. So this is the tangent plane. It's also the linear approximation. So whenever you see a problem that says, oh, you should approximate, the approximation comes from this idea that the tangent plane is an approximation. Of course, we can do better approximations, and we learn to do that with Taylor polynomials. We can talk about the chain rule, where we have functions inside a function. So for example, I could have z is a function of x and y, x is a function of t, and y is a function of t. So in that case, we would have dz dt is partial z partial x, dx dt, and partial z partial y dy dt. If you're going to apply the chain rule, just think about how the variables relate to one another. I like to use a diagram. If I were a computer scientist, I would say it's a variable tree to sort of say how do all the variables connect, and that gives me an idea of how the derivatives relate. And I've already mentioned you can use tangent planes to do approximation. Now, one thing, of course, we talked about which is really important is this vector of the partial derivatives. So partial f, partial x, partial f, partial y, that we called this del f, or nabla f. That's the collection of partial derivatives. This gradient. And the gradient takes a role in many cases of what the derivative was doing for us in Calc 1. So we're going to talk for a second about critical points. In Calc 1, it was, where is your derivative 0? Now, in our mysterious, wonderful world of multivariable calculus, it's, where is the gradient equal to 0? You can also talk about directional derivatives. So if I want to find the rate of change, or also known as the derivative, in the direction u is a unit vector. So when we use direction, we use unit vectors to represent directions. Of the function f at the point P, it's the gradient of f evaluated at P dot u. So the gradient really has all these wonderful properties. It can be used to find directional derivative. And as a consequence, we can do things such as say that the gradient points in the direction of greatest increase. The magnitude of the gradient points in, negative of the gradient points in the direction of greatest decrease. The magnitude of the gradient is the amount of greatest increase. Negative the magnitude of the gradient is the amount of greatest decrease. And as a free bonus, we get that the gradient is perpendicular to level curves and level surfaces. Now, this is a really cool fact because it tells us that if I have a really bizarre looking surface created out of a function where I don't have z equals f of x, y, but I have all sorts of combinations of x's and y's and z's, that I can use the gradient to find something perpendicular to that, which means that can act as my normal vector. So gradients are a great way to find tangent planes. So that's another thing that the gradient can do. Okay, before I jump into optimization, let's talk about two things. You have this notion of mixed partial derivatives. You can always assume that the derivative with respect to x and then with respect to y is the same as the derivative with respect to y and then with respect to x. So in other words, the order you take derivatives won't matter. We're going to give you nice functions to work with. Another thing is we can talk about implicit derivatives. So if you have a function, f of x, y, z equals some constant, well, that tells you that y is related, z is related to x and y. Now, we don't know what the relationship is. That's why it's implicit. There's some relationship, we don't know what it is. But from there, we can extract what it is. So what you do is you simply just take the derivative of both sides with respect to x or with respect to y, and then just remember, this is the hard part you have to remember, that wherever you see a z, you should think of it, well, really, z is a function of x, y. So that is, remember that z depends on x and y. So when you're taking the derivative with respect to x, you're going to get a partial z partial x. And when you take the derivative of z with respect to y, you get a partial z partial y. And these pop out more or less right away. Alternatively, you just memorize the formula. I don't know what's easier for students these days. Okay, last part down here is optimization. Optimization, very important thing that comes out of calculus. So what do? Well, one thing is you have to know the critical points. Critical points, where is the gradient 0? Where is it undefined? Where is the boundary? Now, most of the time when we talk critical points, we really just focus on where is the gradient 0. So to find the critical points, take your partial derivatives, set them both to 0. You end up with a system of equations, and now you get to solve. And this is fun. So the calculus part is not so bad. Then it turns into algebra, a game of algebra. And I love algebra. And you probably don't love it as much as I do. But I hope it's growing on you. It's like, this algebra stuff, it's not so bad. Take your time. Don't panic. Remember, we're not letting you have calculators which says that the answers can't be bad. They have to be reasonable, which tells you, among other things, that really nice things should be happening. And if nice things aren't happening, then there's possibly been a mistake made. Or perhaps you're trying to force it to do the wrong thing. Don't force anything. Relax. You're going to have plenty of time. I think time is not going to be an issue for anybody. Just relax, take your time, let the algebra flow through you. Become one with the algebra. All right, now what do? Once you found the gradient, you might want to classify. So if you ever see a problem that says classify critical points, that really means use the second partials test. So you set up this expression d of ab. Sometimes, by the way, this is called the Hessian, and it's f sub xx times f sub yy minus f sub xy squared. If that value is negative, you're a saddle. If it's positive, you're a max or a min. And to know, you push in and you look at the slice. So you look at fxx or you look at fyy, doesn't matter. If they're positive, you're at a min. If they're negative, you're at a max. If you get 0, the test is inconclusive. Just stop. Don't even have to go any further. You don't have to go any further. All right. Now, the other thing is you could have optimized fxy given a constraint. G of xy equals a constant. This is what we talked about last time. Lagrange multipliers. Okay, how do you do it? Set up a system of equations. Gradient of f equals lambda gradient of g, g equals c. You're going to solve that. When you solve for that, you find the points, the good points. Those are the points you're after. Now, how do you solve for that? Well, I have some advice. When in doubt, solve for lambda. It works great. That has gotten me through like every single Lagrange multiplier problem I've ever had to do. And it'll work for you if you see it. Who knows? I know, but you'll know on Friday. Once you have the point, well, you plug it in and you interpret. Okay. Finally, we can talk about optimization on a closed bounded set. For that one, it's a little bit fun. It's making a list. So you start by making a list. You check in the interior. Where's the gradient 0? You look on the boundary. And sometimes that can take a while because you might have lots of pieces on the boundary. You got to check each piece. Okay. After you've checked each piece, you evaluate all the points you found. So this is, you're making your list. Now you're going to check it. Whichever is the largest number on that list is your max. Whatever is the smallest number is your min. All right. And I think that's about everything. Did I miss anything? See, that's not so bad. One page. One page. Now, this will, by the way, as with all notes, be scanned online. So, all right. If there's no questions, I thought we could work some problems. Okay. All right. We'll start. So these are various problems from old exams, and chosen because they look like they might be fun. I hope they are. We'll find out. Okay, so here's a problem from an exam from a long time ago, spring 16. So consider the function f of x, y, z. It's x squared plus 3xy minus z squared plus 2y plus z plus 4. And there's two parts. Part A, find the direction where the function f increases most rapidly at the point 1, 1, 0, and compute the rate of increase along that direction. Now, when you see this increases most rapidly, that says, okay, what does something most rapidly? Gradient. You know, one of the things that's hard is you know a lot. And you might think that's a good thing. That can also be a bad thing, is because you know so much, you know too much. And you have to start knowing, okay, how do I know what of my many awesome tools to apply? So this is a gradient problem. So we're going to find gradient of f. Okay, so what is gradient of f? 2x plus 3y, comma, 3x plus 2, comma, negative 2z plus 1. Okay, that's gradient of f. Now what do I do? Well, I have a point. Probably I'm going to do something with that point, and in this case, I'm going to evaluate gradient of f at that point. Gradient of f at 1, 1, 0. So I put in x equals 1, y equals 1, z equals 0. 2 plus 3, 5. 3 plus 2, 5. 0 plus 1, 1. 5, 5, 1. All right. So that's the gradient. Now, what's the direction? Well, the direction, we could argue it's a vector. Okay, that's a direction. Now, they might have said unit vector, but here's my rule of thumb. If they didn't say unit vector, you don't have to put a unit vector. Okay, so that's the direction. What else do we need to do? Well, there's an also. Rate of increase in that direction. How do we find that? Magnitude of the gradient. So magnitude of the gradient at 1, 1, 0. That's the magnitude of 5, 5, 1, which is the square root of 25 plus 25 plus 1, because I square each entry, which is square root of 51, which is square root of 51. It's the answer. Rate of increase. Okay, that's part A. Cool. Part B. Well, it says find the directional derivative at the same point in the direction of the vector 2i minus j minus 2k. So u is 2i minus j minus 2k, which, by the way, if you like, you can write that as 2 minus 1 minus 2. These are the same thing. Work in whatever you're comfortable in, but be willing to adjust. Yes?
Why did you know direction was to the left?
What do you mean by the direction was to the left?
Your arrow? Or just
No, I'm just saying the direction is this thing. I'm pointing at, this is my answer.
okay.
That's what I'm trying to say. Yes. I'm sorry. Let me squiggle it. There we go. The direction is that way. Okay. Now, what's wrong with this direction vector? Not a unit vector. So what do we do to it? Make it a unit vector. So we find the magnitude of 2 minus 1 minus 2. That's the square root of 4 plus 1 plus 4. Square root of 9, also known as 3. So we have our vector u is 1/3, 2 minus 1 minus 2. What do we do with that? Take the dot product with the gradient. So we take 5, 5, 1, dot 1/3, 2 minus 1 minus 2. So that's 1/3. 5 times 2 is 10. 5 times 1, that's minus 5. 1 times negative 2 is minus 2. 10 minus 5 minus 2. 3 times 1/3 is 1. And that's the answer. Ah, man. Great problem. Great problem. Nice one to warm up on. Okay. Let's try another one. Here's another one. Find all points, x, y, at which the tangent plane to the surface z equals x squared minus 3xy plus 5/2 y squared minus 2x plus 3y is parallel to the plane given by the equation 2x minus 4y plus z equals 6. So I want to find when is a plane, tangent plane here, parallel to a plane here. Well, how are we going to figure that out? Carefully. I like that answer. I like that answer. Now, there's a couple ways to figure this out. Here's what I would do, and I'm somewhat biased. As I would think about this plane. Now, I could do one of two things. One thing I could do is I could say, well, hey, the normal for this is 2, negative 4, 1. And to be parallel, I really need to have more or less the same normal, up to some constant. Yep, that would be true. Another way I can think about this is to say, well, look, this really says z is equal to minus 2x plus 4y plus 6, to rearrange it. And if I come over here, what do I have? Well, I have that a tangent plane looks like what? If I think of the left-hand side, if I have z equals f of x, y, a tangent plane will look like z equals f sub x at AB times x minus a plus f sub y at AB times y minus b plus f at ab. That's what a typical tangent plane looks like. But now, if I really think about what's happening here, I say, you know, here I have z equals, here I have z equals. So what I need to make sure, this plus 6 doesn't change the tilt of the plane. So essentially, this constant, if I change this 6 to a 7, I'm still parallel. I'm just moving it up or moving it down if I change it up or down. So it's these negative 2 and 4, these coefficients, that's what determines how the plane tilts. So if I change those, I'm affecting the tilt of the plane in one or the other direction. So those are the important things. So really, I say, aha, if I look at the coefficient for x in this expression, what is the coefficient for x? Well, it should be this piece here. That's the coefficient for x. Well, what do I need this to be equal to? I need that to be negative 2. And here, this will be the coefficient for y. What does that need to be equal to? 4. So really, this problem says I need f sub x at AB to be equal to negative 2, and f sub y at AB need that to be equal to 4. All right, well, what is f sub x at AB? Let's go through it. What's the derivative? 2x minus 3y minus 2. Down here, negative 3x, 5y plus 3. Now, as we go through here, you'll notice, oh, hey, the negative 2's cancel. So this says that 2x is equal to 3y. Down here, you'll get 3x plus 5y, negative 3x plus 5y equals 1. Now, we got to figure out how to solve this system of equations. How do we do it? Well, lots of ways. If I multiply here, say by 2, I'll have negative 6x plus 10y equals 2. And then I say, oh, hey, notice that 6x equals what? Equals 9y. So minus 9y plus 10y equals 2. So what does that say about y? Y equals 2. If y equals 2, coming back into here, I get that 2x equals 6. So what is x? X equals 3. And so the only point, all points is 1 point. It's the point 3, 2. And there we go. So you should be comfortable with tangent planes and working with tangent planes. You are essentially guaranteed a tangent plane at some point will show up on the test. So be comfortable with what they are and how to work with them and all their different ways you could possibly work with them. All right. How am I doing? Do I need to slow down or speed up? I can slow down. It is possible. I have lived in the Midwest long enough. I have learned to be slow. So, no. I'll have you know, I was born in the Midwest. I was born in Chicago. So, you know, that's my roots. That's my roots. So, okay. So, next one. Here we go. An implicit function. So we have an implicit function, z, in terms of x and y. So x to the 4th plus y squared plus z to the 6th equals 3xz. I cannot solve for z. It might even be impossible to solve for z. I'm not entirely sure. But I can't do it. Okay, so what are we going to do? Well, we're just going to have to work implicitly. So I want to find the expressions partial z partial x and partial z partial y. And there's a note here that these can involve x, y, and z. So in other words, look, when you're solving for implicit functions, don't feel like you have to somehow eliminate variables. No, it's okay. They'll have all sorts of things. So for part A. Well, this is one of those implicit things. So really, you should say, oh, hey, when I think of z, I'm going to think of z as depending upon x and y. Now you might say, well, couldn't I also say that x depends on y and z? The answer is yeah, I could do that. But because I'm taking the derivative of z, see how z is in the numerator? That's what I want to say. That function depends on the other ones. So I want z as a function of my other variables, x and y. So what do I want? Well, I'm going to take the derivative with respect to x first, and then I'll take the derivative with respect to y. I'll do these separately. So I'm going to take the derivative with respect to x. I'm just going to work my way across. So derivative of x to the fourth with respect to x, 4x cubed. So just here's a side note, derivative with respect to x. So 4x cubed. Derivative of y squared with respect to x, 0. Derivative of z to the sixth with respect to x, 6 z to the fifth times the derivative of z with respect to x. Now, why is that not 0? Because in the implicit relationship, z is depending on x. X and y are considered to be independent. So x and y can do whatever they want independently of each other, but z will move with them. So z depends on x. Is equal to what? Well, what rule do I need to take that derivative? Product rule. So what's the derivative become? 3. Okay, so I can take the derivative, I can take the first times the derivative of the second plus 3z. In that case, here the derivative was I took the derivative of x. Derivative of x with respect to x is 1. Once you are at this stage, then the rest of it is fairly simple. You move the dz dx's to one side, things without dz dx to the other side. So you get 6z to the fifth minus 3x. That all is being multiplied by dz dx, our partial z partial x, and that equals 3z minus 4x cubed. And finally, what do we do to get dz dx by itself? Well, we divide. 3z minus 4x cubed over 6z to the fifth minus 3x. Okay. And we're done. That's dz dx. Okay, part B, well, A prime, I guess I should say. We should do partial y. Forgot about that. Okay, derivative with respect to y. Derivative of x to the fourth with respect to y is 0. Derivative of y squared, 2y. Derivative of z to the sixth, 6z to the fifth times derivative of z with respect to y equals, what rule do I need to take here? Well, because we're taking it with respect to y, so the derivative will be, yeah, I don't need to take a product rule here. And you might want to say, well, why not? Well, because the x is treating as a constant at this point. It's independent of y, so I don't need to, it doesn't change with y. Okay, move stuff around. I'll go ahead and move this across, I'll move this across, and we get that dz dx. Times 6z to the fifth minus 3x. My handwriting is getting bad here. Equals negative 2y, or partial z, partial y. That's an y, sorry. Partial z, partial y is negative 2y over 6z to the fifth minus 3x. And there we go. All right, so there's our derivatives. You'll notice that these denominators are the same. That's not a coincidence. If you go back and look at the actual way we talked about finding implicit derivatives, we have f of x, y, z equals a constant. Then you have the same denominators. Now you might say, well, this doesn't fit f of x, y, z equals a constant because I have pieces on both sides. Well, what do I do? If I want to write this as f of x, y, z equals a number, can it be done? Or is it just impossible? Maybe it's an impossible thing? Maybe it's possible? Anyone? Anyone? So in other words, can I shove all the variables on one side? Is that possible? How do I shove all the variables on one side? Yes, I do this very fancy thing called subtract. And I can shove all the variables on one side. So, don't get thrown off if we write it in a different way. Because we can rewrite it. That's the cool thing. In math, you can rewrite the problem to make it easier. It's also true that you can rewrite it to make it harder. I discourage you to use that approach on the exam. That's our job. Our job is to make the problem harder. Okay, part B. Find the tangent plane to the surface of this function at 1, 1, 1. Well, what do I need to know to find the tangent plane? Well, I need to know the derivatives. That's one way to do it. Do I know what the derivatives are at 1, 1, 1? They're right here. So what do I have? Well, I would say that my tangent plane would be equal to the value of z at that point. Well, there it is. It's 1. Plus the derivative of z with respect to x at that point. Now, it's not a function. What do I need to do with this? I evaluate. So I plug in 1. I get 3 minus 4 over 6 minus 3. So 3 minus 4 is negative 1. 6 minus 3 is 1. The nice thing is 1, 1, 1 is a very easy point. Times x minus 1 plus the derivative with respect to y. Well, that's minus 2 over 6 minus 3, negative 2/3, times y minus 1. So essentially what I'm saying here is you're thinking of z as being a function xy. So it's your function at that point plus your partial derivative with respect to x times x minus a plus your partial derivative with respect to y minus b. So you can extract it from this information. That's one way to do it. It's not the easiest way to do it. We could do it in an easier way. Is there an alternative? I'll call this B other, or bother, if you will. So is there a bother here that we could do? And someone said it, I think someone over in this general area. Gradient! Yes! You got it. Okay. You should say it with more confidence next time. Because almost always the answer is the gradient. So, all right. Now, how do we find the gradient? Well, remember, if you can ever write something as f of x, y, z equals a number, tangent planes are awesome in this case. Now, can we write this as f of x, y, z equals the constant? Yeah, we already did, because we moved everything to one side. Okay, so what is the gradient of this function? So this left-hand side is capital F. Gradient is 4x cubed minus 3z, comma, 2y, comma, 6e to the fifth minus 3x. Now, what do we do with this gradient? Evaluate it at the point 1, 1, 1. Gradient f 1, 1, 1 is 1, 2, 3. Nice numbers. We like those numbers. That is our normal vector. So this is going to become x plus 2y plus 3z equals something. What is the something? Yeah, it's the point 1, 1, 1 into here. 1, 1, 1 into this gives me 6. Now, I will tell you, this plane is the same as that plane. If you multiply this plane here by 3 move stuff around, this becomes that. They're equivalent. Which one would give you full points? They both would. Look, we're not trying to say, read our minds and give it to us exactly like you want. We are smart enough that we can say, oh, you did correct work. Correct works, full points. That's what we want. All right. Cool. Let's do another one. Find the maximum and minimum value of f of xy equals 2x plus 3y plus 2, given that 2x squared plus 5xy plus 4y squared is equal to 28. Now, what is this? This is a constraint. So we are trying to optimize, and the reason we know we're trying to optimize is because we see the words max, or we see the words min. So whenever you see max or min, that's optimization. Whenever you see a constraint, you're saying optimization with constraint. What tool do we have to do optimization with constraint? Lagrange multiplier. So there are clues in the problem about what it wants you to do. Now, sometimes the clues are a little bit more explicit. For example, it might say, use Lagrange multiplier to ... If you see that, do that. If you don't see that, well, sometimes you have to extract the information. Okay, so this 2x squared plus 5xy plus 4y squared, that's g of xy. All right, now what does Lagrange multiplier say? Yeah, the gradients have to be parallel. The gradient of f is lambda gradient g, and the constraint is satisfied. So what we're going to do is we're going to focus on this gradient of f equals lambda gradient g. From there, we're going to extract a relationship between x and y. And we're going to mix that in with our constraint, and hopefully good things happen to us. So gradient of f equals lambda gradient of g. That says f sub x equals lambda g sub x, and f sub y equals lambda g sub y. Well, what is f sub x? 2. That equals lambda times g sub x, which is 4x plus 5y. All right, f sub y is 3. Well, that's going to equal lambda times g sub y, which is 5x plus 8y. Now, here's the thing. We don't really care about lambda. We care about x and y. But we have to solve for x and y, and somehow we have to use lambda. So, what should we do? Yeah, when in doubt, and hopefully you'll have lots of doubts, but when in doubt, solve for lambda. It works really, really well. It's like the ideal thing to do. So what do I mean? Well, we get that lambda, if I take this first equation, is 2 divided by 4x plus 5y. From the second equation, it would be what? 3 divided by 5x plus 8y. Now, the cool thing is these are both equal to each other. So what can I do next? Cross multiply. 10x plus 16y is equal to 12x plus 15y. Now what? Yeah, I can move stuff around. 16 minus 15 gives me y. 12 minus 10 gives me 2. Y is 2x. So, from the gradient of f equals lambda gradient g, I have this cool relationship that y is twice x. What do I do with this information? Plug it into the constraint. So our constraint, remember, is over here. 2x squared plus 5xy plus 4y squared equals 28. So I'm going to rewrite that. Everywhere I see a y, I'm going to put a 2x. So I have 2x squared plus 5x times 2x plus 4 times 2x squared equals 28. All right, well, that's 2x squared plus 10x squared plus 16x squared equals 28, which becomes 28. X squared equals 28. Yeah, x squared equals 1, so x equals plus or minus 1. So that leads to two possibilities. So there's a point, 1 comma 2. There's another point, minus 1 comma minus 2. You're probably saying, well, where did these numbers come from? Remember, we were already told that y is 2x. So once I knew x, I doubled. That gave me y. Now, I am finding where the points could be. We are not going to do something silly where we're going to ask you for a max or a min, and then they're not actually going to be there. It's going to be at the points that you find, which is good. And so among other things, if you only find one point, that's the point. If you find multiple points, you just test multiple points. So we found multiple points. But that's okay because we're looking for multiple things, max and min. So what do I do with these points now? Plug them in. Okay. So I'm going to plug in 1, 2, and minus 1, minus 2. If I plug in 1, 2, I'll get 2 plus 6 plus 2 is 10. If I plug in minus 1, minus 2, I'm going to get minus 2 minus 6 plus 2, which is minus 6. Now, how do I interpret it? What is 10? Yes, that's the max. What is negative 6? That's right. That's the min. So there we go. Max, min. Done. And that's done. We found the max and min value. Okay, good. We're doing great on time. Let's do another one. Oh, I love this one. I love this one. Not this particular problem, but find and classify. I love these kinds. Yes?
Go back to that.
Sure.
You taught us that. You said you used an example. You said the max and min.
I know. Wasn't that great?
Yeah.
Because they were there. It was a dark day in 2011. I think it was a Tuesday, and like I said, we won't do that to you. We won't do that to you. So don't worry about that. We're nice people. You know, several of the people involved in that test have since retired. So, you know, they're no longer with us. They're they've been put out to a mathematical pasture where they spend their mornings taking derivatives. And but anyways, here we go. So find and classify all three. I don't know why they told us there were three, but okay. All three critical points of h of xy equals 4x cubed minus 6x squared y minus 3y squared plus 12y minus 7. So this is a find and classify. So there's two stages. There's the find stage and there's the classify stage. Now, you should always do the find first because you can't classify if you don't have anything. So you actually have to find. So first to find, what do we do? Right, we find the gradient, or we also can say, do what? Take partial derivatives and do what to those? Set everything to 0. So either set the gradient equal to 0 or set the partial derivatives equal to 0. That means the same thing. So let's talk about partial derivatives. H sub x. What is h sub x? 12x squared minus 12xy. Oh, and that's it. Oh, okay, great. Equals 0. All right, h sub y is negative 6x squared minus 6y plus 12 equals 0. Now, I should tell you that there is not a universal way to solve these problems. This is now algebra. It's a matter of manipulation. Just be careful and don't make silly mistakes. And you're probably thinking, I would never make a silly mistake. Here's an example of a silly mistake. I could say, hey, check this out. Now remember, this is me being silly. Hey, check this out. This 12x squared minus 12. Let me change colors, just to emphasize. I'm going to choose pink. It's a very silly color. All right. Look, this here says that 12x squared equals 12xy. Well, both terms have a 12x in them, so I'll just go ahead and cancel a 12x, and get that x equals y. Yeah, that's pretty cool. All right. Have I done something bad? Yes. Now, this first step is totally legal, but silly. You shouldn't have done it. This second step is immoral. What did you do? You lost at least one, possibly more solutions. Why? Yeah, because I divide by x, but x could have been 0. I lost the possibility of saying that x is 0. So never divide to cancel if it could be 0. Because if you do that, you might lose a solution. Okay, so, all right, now let's be more realistic. What would we actually have been doing? Oh, we should go back to blue. Yeah, I would just factor. Factor is a great thing to do. Factor out of 12x. X minus y equals 0. So what do we really have? Well, a bunch of stuff multiplying together. So either x equals y or x equals 0. Perfectly fine. Now what do I do with these two pieces of information? Plug it in. Suppose I said x equals 0. Then I get that for hy, I'd have minus 0. So that goes away. Minus 6y plus 12 equals 0. What does that say about y? So that says y equals 2. Thus we get the point 0, 2. On the other hand, if I said x equals y, so here what I can do is everywhere I see, I'll replace the y by x. So minus 6x squared minus 6x plus 12 equals 0. Now obviously let's factor out the minus 6 just so we can see it more clearly. X squared plus x minus 2 equals 0. Now how can we work with this x squared plus x minus 2? We can factor. Yes, you should, I hope, be convinced that things will unreasonably factor in this class. This should be a sign. If you get to something which doesn't factor, go back. Because something happened. Because we're nice people. We'll give you things that factor. What does this factor as? X minus 1 and x plus 2. Giving us what? Well, x equals 1 or negative 2. Which leads to the points, because remember we also said x equals y, 1, 1, negative 2, negative 2. Okay, so we have our 3 points. 0, 2, 1, 1, negative 2, negative 2. Those are the points that we have found. So check that off. We're not done, but we've made good progress. We found them. What comes next? Classify. Okay. And to classify, we go and we start looking at hxx, hyy minus hxy squared, which I call d. If you are in a different class, sometimes this is called the Hessian, but that's okay. We call it just d, discriminant. All right, well, let's compute these. What is hxx? Yeah, 24x minus 12y. Hyy. Minus 6, that's promising. Minus hxy. Negative 12x. And we square it. Okay, d of 0, 2. Well, that's negative 24 times negative 6 minus 0 squared. What can we say about that? It's a positive number. Do I care about the fact that it's equal to 144? No. I only care about the fact that it's positive. It's positive. Well, what does that tell me? It's either a max or min. So I don't have quite enough information alone from D to say max or min. But what do I know? Well, I know that hyy is negative 6. And it's always negative 6. So what does that allow me to conclude? 0, 2 is a, yes, max. Good. Now, 1, 1. Okay, so I'm going to get 24 minus 12 times negative 6 minus negative 12 squared. Okay, what can I conclude? It's negative. Now, do I care about the fact that this is equal to negative 216? No, I don't care that it's negative 216. I just care that it's negative. What does that allow me to conclude about 1, 1? Yes, I can conclude that this is a saddle. And I know I'm just a little bit over it, but let's finish this. Finally, negative 2, negative 2. If I plug in negative 2, negative 2, that'd be negative 48 plus 24, which is negative 24. Wow. Okay, times negative 6 minus, okay, then it's negative 2 times 2. That's 24 squared. Negative 24 times negative 6 is a big number, but not as big as that number. So this is negative, and so this is also a saddle. And okay, good. All right. Whew. All right. Study hard. You'll be okay. Test is on Friday. Good luck.